introduce our speaker, Andrea Thomaz. Andrea is an associate professor at the University of Texas at Austin in the Department of Electrical and Computer Engineering. She's also the CEO of Diligent Robotics, and I think she'll be telling us a little bit about both her research at UT and her work at Diligent in this talk. At UT, Andrea holds the William J. Murray Jr. Fellowship in Engineering. And at Diligent, as I said, she's CEO. Her work at Diligent has looked at developing AI for socially intelligent robots, including a robot called Moxie, which is an autonomous assistant for healthcare practitioners in hospitals. Andrea's research in general is on AI, robotics, and human-robot interaction. She builds computational models of the mechanisms of human social learning, and uses that to build social robots and machines that everyday people can teach. Andrea has a lot of awards, so I'm not going to talk about all of them, but she's been honored with an NSF CAREER Award, an ONR Young Research Investigator Award. She's been put on Popular Science's Brilliant 10 list, and also MIT's 35 under 35. So with that, please welcome Andrea.
Thank you, honey. Excellent. I'm very excited to be here today and tell you a little bit about what we're doing down at UT Austin. And I'd love to introduce you to some of the students and robots that I've had the chance to work with over the years, over the last 10 years, really. So our research is really focused on building, machines that a human can be side by side in the same working space. So we're usually thinking about, how we can have robots and humans kind of performing actions together, and the robot kind of socially appropriately responding in this kind of physically co-located space. And over the past 10 years, the robots my lab have developed have interacted with hundreds of people. And so, we're usually interested in making sure that our robots are interacting the way an end user is going to expect, and it's a key part of our research. Our goal is for robots to be more like a teammate that's lending a hand, and not something that you have to think about as like a tool that you have to command. So we're interested in thinking about how we can get robot teammates to be something that's very seamless and feels natural to interact with. And so, what is hard about this is, we can think about, in our vision for this is a perfect robot teammate. What would that look like? We can think about an example like this one, where you have this group of people that came together. This is actually a picture that I found on the web of a disaster relief effort. And so this is kind of an ad hoc team that came together, and they're building furniture that somebody picked up, and then somebody else you could imagine joining this team, and you would easily say, oh, what needs to be done? And somebody would quickly tell you, like, oh, go grab those things over there. And then if you didn't know how to make the little tables, and somebody would quickly show you, and you would do a lot of learning on the job and perceiving whose turn it is. So this is a really hard problem, and so we can think about all of the things that are computationally hard about adding a robot to that kind of functioning, seamless, ad hoc, learning on the job team. And that's the way I like to frame the kind of what we call the engineering challenges of successful human-robot interaction. So this is the way I like to think about human-robot interaction being, some really hard and interesting computational problems that we have to solve in AI and computer science and engineering in general. So we have to get, the robot to be able to perceive the multimodal behavior that's going around in this space. So that's a very hard computer vision problem. We have to plan dynamic joint actions, and so it's a hard control problem that we're coordinating our actions with others. We need to generate multimodal dialogue to coordinate the activities of others. So a lot of how everybody's getting on the same page in this ad hoc team is through dialogue and coordination. And like we were talking about, we need to maybe jump in and learn things on the job. So there's nothing about this specific situation that would necessarily be pre-programmed into a robot. It's going to need to be able to adapt and learn on the job. And by the way, it all needs to happen in real time. So this is why I think that HRI is one of the most exciting and fun problems to be working on. This is why I've been spending the last, however many years of my career working on it. And today I'm excited to tell you guys about some of the, focusing mostly on the learning aspect of this and how learning on the job is a problem that I've been focused on for a while, and a lot of the things that my group thinks about. So we think a lot about this notion of adaptation and the fact that a lot of successes in robotics are in structured environments where you can program once and then repeat. Not all successes, but there's a lot of them. And so if we're designing robots for human environments and to be around humans, that is just by the nature of people being noisy and hard, that creates a lot of dynamics where pre-programming controllers is no longer an option, and we have to think about how we're going to get the robots to do what we need them to do in these environments. And so my answer to this and the work that my group likes to think about is how a robot can learn from human teachers. So it learn from demonstrations, learn from the people that it's out there needing to serve. So you have a service robot going out into the world, into a dynamic human environment. It needs to have the tools and capabilities to figure out what it's supposed to do from the people that it's serving. And so one of the primary ways that we're thinking about that is through demonstrations. But one of the things that my lab's been one of the questions I think that's been driving a lot of the work in my lab is what is it that a robot should really be taking away from a demonstration? So what is the demonstration? And what is the information that a person is trying to communicate to the robot by that demonstration? So here's one example of some work by a former Ph.D. student, Barish Atgun. And this is where we have our robot Curie that's learning how to, let's see. Oops.
Start here. Okay. Go here. All right. Go here. Yes. And here. That was demo number 3.
So Kalisha gave a keyframe demonstration showing a few points along the way that Curie needs to hit in order to open this box. And so in this work, Barish was having the robot learn 2 things from that demonstration instead of the typical one. So in one case, it's learning the motor positions that it needs to go through in order to execute this particular action. But it's also got a perceptual model of the scene. In this situation, it was an overhead RGBD camera that was looking at this single referent object and tracking it. And it's building up a goal model of that object that I'm interacting with and looking at, through those keyframes, how is it changing. And so I have a demonstration that's multiple keyframes, and then at each keyframe I'm learning a multimodal Gaussian distribution over the perceptual space and the action space. So I'm actually building 2 graphical models separately to say I have a way that I'm going to do the action, and then I have an expected perception that's going to be happening at the same time. And so then when I'm monitoring an execution, what happens is I'll sample the action model in order to find the set of keyframes that I'm going to be going through to execute a trial. And then as soon as I hit the point in time that the keyframe existed, I'll take a snapshot of the world, and that'll be my first observation in this goal sequence. And at each keyframe, I can take a snapshot of the world. And so now I have my execution and a sample in my sampled observation of the goal, and I can ask my goal model, was this a success, or does this look like the successes that I've seen? And so here's what that looks like. Why is this not playing right?
Show me what you learned. I will gladly. How did I do? That was a success. All right.
So this is earlier in the demonstrations where it still doesn't know if the perceptions that it's built up in that goal model are success or failure. So it's asking, since the person is around, saying, was that a success? Should I add this to my sequence of things that success looks like? And Kalisha says yes. But if it's unsuccessful, then it's time to practice. So what's interesting about that is it got a demonstration from a teacher, and it recreates the action, but had a good enough perception model of what was supposed to happen to say, I think I failed. And so now we have this ability to self-supervise some practice to that action model, some changing of the Gaussian distributions over those poses in that sequence in order to fit something that would succeed.
Try again.
So here it's now sampling further away from the means of those Gaussians in order to get.
Try again.
So what in this behavior is reference to the box rather than in robot joint angles?
So the end effector pose is with respect to the centroid of the box. So it's learning the pose with respect to the centroid of the box. So after it practices and has a larger distribution of success and failure, then it's got a final model that can close the box. And so it's interesting here because we have now a human demonstrated action model that was completely failing. So here's like case studies of 5 different participants that taught this action to the robot. And in all these cases, you run the action model that they taught 5 times, fails every time. But from those same demonstrations, the robot was able to build an appropriate model for what success looks like, and that model of the goal was able to self-supervise an exploration process around the pose distributions that the person demonstrated in order to get to success every time. So we think this is interesting because the robot is now, and it gets back to this question of like, what should the robot really be taking from a human demonstration when that person is a kind of novice end user? And people are much better at demonstrating the goal of what you should be doing than maybe demonstrating exactly how it should happen. And in particular, this robot has series elastic actuators, and there's some noise. It's hard to demonstrate kind of compliant actions, and so it's easier for the person to demonstrate the goal and let the robot figure out, seated with a kind of noisy demonstration, how to actually get it done. So the thing that I'd like to talk about next, so that's kind of a little bit of Barish's work kind of sets up this interesting problem of how we should make efficient use of people by having the robot kind of practice and explore. But it still is really intense, right? The robot is practicing in the real world, which is expensive and dangerous. And so now I want to highlight some 3 different projects in recent work that are really aimed at this efficiency of human in the loop learning. And so getting to where we can learn either more realistic tasks, or we can learn tasks in more real time, and that's kind of I have 3 students that's been one of their main focus. So I'll talk about some attention modified policy shaping, talk about leveraging simulation, so all of that practice doesn't have to be happening in the real world, and then some recent work on tool task transfer with corrections instead of learning from scratch. Okay, so the first is some work that's with my student Taylor Kessler-Faulkner and postdoc Elaine Short. And in this case, we're working in a reinforcement learning domain where the robot is using policy shaping. So the signal from the person is not a reward signal, but is influencing action choices. And the robot is building up a model of what the human thinks is good and bad action choices. But what Taylor's really interested in is the fact that an agent that's learning from a human, a robot or otherwise, is usually assumed that teacher's always there and that teacher's always paying attention. And but in the lifelong learning sense, we have to think about when the person might not be paying attention or they might get distracted. So how can we build algorithms that actually care about or take into account that attention and whether or not somebody's there. And so if the change that she made is developing an approach that modifies the exploration strategy depending on whether or not a person is paying attention. So it keeps a model of which state action pairs the person has actually seen and which state of action pairs the person has given good or bad feedback to. And then we can have, when the teacher is paying attention, the robot chooses between the actions that the person has not seen and the ones that are good. And when the person is not paying attention, we can be more conservative. So let's see, oops. There we go. So with less attention, when the person is not there, the robot is trying to learn how it can move this cup around the table and the goal is to keep the cup on the table and it stays more conservative with less attention. But when the person's there, we also take the opportunity to explore actions that we've never seen, like trying to push the cup off the table in a situation that the person is there to give feedback. And so what happens is that in this graph we can see that the green sections show presence of attention from the human teacher, and we're looking at just general policy shaping versus attention modified policy shaping. And what happens is that increasing exploration causes the agent to collect less reward when being supervised. Overall, it speeds learning and allowing the robot to make more efficient use of the person. So we see that when the person is not there, so we're getting less reward, or we're getting kind of reward that's similar to regular policy shaping in the green sections, and that's because the robot's doing all of these terrible actions, like trying to push the thing off the edge. But then as soon as the person disappears and we're exploiting that policy, we see that it's significantly better than what we were learning with just straight policy shaping. Okay, so that's one example of adding to the efficiency, making good use of the human teacher and efficient use of the human teacher. Next thing I'd like to tell you about is some exciting new work from one of my students, Adam Elevato, who's thinking about leveraging simulation in the loop. And so in addition to thinking about the robot learning on its own and practicing, we want to think about how you might use a simulator to augment some of the things that the robot's learning. So for example, back to that box opening, it would be great if the robot could take a single example with that box and then go off and practice in a simulator, and then come back and be perfectly ready to go. But one of the biggest problems that we've had with trying to apply simulators in a learning problem like this is really, the objects, and that your physics simulator is never kind of exactly tuned to the real world. And you can go off and you can simulate things, and unless you're just simulating things about yourself, maybe the robot has a really nice model of itself, but often that's not even the case. But getting the simulator to match the real world well enough that it can be a real tool is one of the kind of biggest bottlenecks. And so this is really the point of Adam's work, is he's thinking about how do we tune a simulator quickly in order to make it relevant to the current situation and the current objects and the current dynamics. And so he's built a system called TuneNet, which is under review. But the idea is that simulators are this powerful tool for task learning, and newer approaches that do think about tuning simulators are usually sample-based. You're sampling a whole lot of data in order to tune the simulator, or you're kind of doing a lot of different environments, or maybe kind of perturbing environments in order to tune the simulator. But what we do is begin with a real environment and a candidate simulator, and then you can, generate observations from the simulator and the real world. And then we use our network a trained network to tune that simulator to be to update parameters. So in this case, the parameter of the simulator that we're trying to get to match the real world is this this coefficient of restitution of this ball, like how it's gonna bounce, which has to do a lot with like the ball, the surface, but a lot to do with the ball parameters that you put in the simulator. And so we can continually update those until it matches our real world environment well enough. And now we have our tuned simulator. And so in practice, we can do this tuning from a single real example, then you can make it match your simulator, and then you're ready to go. And then now you can use this tuned physics simulator with this specific object to now go off and do plans in the world with this particular object. So we did experiments where we tested this on physics prediction tasks and system identification. But the one that we, the fun one, is to take and do that ball dropping to tune your simulator to have the correct parameter for that coefficient of restitution for a ball. And now I should be able to plan bounce drops into basketball hoop, if this will play. No, we want to see the results first. Okay. So again, we had one video of the ball bouncing that we used to train our simulator, and now it can take and decide exactly what height to drop this ball to get it in the basket. And we can do that quick retraining of the physics parameter for whatever ball you want to do. And so now I just have to, drop that ball one time in order to be able to use that ball in a lot of different ways in the environment. So we think this is really exciting. And one thing that we did notice, so there, doesn't work every time. So it's interesting to look at what the failure cases were. And with this was an irregular ball that didn't work every time. But it turns out that the main problem with this ball is that it bounced all the way off the table during the training phase, such that in that tuning we didn't get enough of the training to tune the parameters more than 3 times through. So that's a problem that we're working on, but it's interesting. And the takeaway of TuneNet is that it's able to do this problem kind of hundreds of times faster than one that's going to need a huge amount of data. And the real kind of insight is that you can have a network built, this TuneNet, that is really built based on you can even use two different simulators, and you're kind of learning to tune one to the other. And that process, that network that you build that's able to tune one simulator to the other, can now then be replaced and can tune the simulator to the real world, tune the simulator to another environment, and it just needs the one example to do it. And Yeah, so the thing that we're really excited about is that we only need one real-world example to train it, and that we can, and the network is actually training the output of one simulator to match the output of the other. And what's important about that is that the actual, parameter, the actual kind of coefficient of restitution that you need to set in your simulator may actually be really different than the true physical parameter. So, even if you knew the true physics of the world, coding that into your simulator doesn't always help. And so, what this does is sort of bypass that altogether and say, let me look at the, what the output looks like in the real world and what my simulator output looks like, and just keep tuning that coefficient of restitution until those match, and now I can go off and use it. Great. So the kind of third efficiency project I wanted to talk to you guys about is a project with Tesca Fitzgerald, who is thinking about transfer learning. And here we're really interested in, again, how we can make really efficient and effective use of a human teacher. And the fact that in robot learning, we often are always learning from scratch. And it doesn't, it's not a very effective use of the person if every time I have to learn something new, we have to learn it all from scratch. And so Tesca's really excited about trying to get robots to leverage things that they've learned before in order to get those to speed up the next phase of learning. And so in this example, we're specifically looking at tools and the use of tools and how you could transfer tasks between tools and transfer tools between tasks. And here she's using a human-guided trajectory adaptation for tool learning. So in this case, the robot receives keyframe demonstrations on a few different tasks. So we have a sweeping task, a hammering task, and a hooking task. And the tool can be imaginatively used to solve each of these tasks. Hammering is what it's made to do, but you can also turn the hammer and sweep, or you can turn the hammer and hook. And so this kind of creative application of one tool for a new task is what Tesca was interested in, getting a robot to be able to learn that kind of transfer of a skill from a person. And so what we're looking at is tasks are demonstrated using one of three tools: the hammer, the paintbrush, or this wrench. And then we get corrections on a replacement tool. So you can replay the original demonstration of sweeping with the paintbrush. Oops. And while you're replaying that demonstration that you would have done with the paintbrush while you're holding the cup, the person can stop and give you corrections to show you, like, no, when you're using the cup, your arm needs to be like this. And so each time that you're getting one of these corrections, you're recording kind of the pose difference between the original demonstration or the original trajectory with the other tool and the new trajectory that I have to do when I'm holding this new tool, this cup. And so then we're building a model of all of those pose corrections to come up with an average. So given a keyframe demonstration with k keyframes with tool A, then we get k corrections with tool B, up to k corrections with tool B, and we can build a corrections matrix and understand how this task needs to be changed from an average. So it needs to, on average, the representation is that I'm going to change some kind of translation on average and some kind of orientation on average. And what's exciting about this, so here we have, we are representing both translational changes and orientation changes, and there's some tasks for which the rotation matters more, and some tasks for which the orientation matters more. So this, pulling of the cup, we see that all of the pulling, hooking the the bucket, we see that the tool is required to be in the same orientation, but maybe the translation of how far down you're hooking doesn't matter as much. Whereas with the sweeping, it matters a lot, like exactly where on the surface of the bucket your tool ends up, but the exact orientation of the tool has more variance, because you just need to be touching the top of the bucket and sweep across the top. And so this is the kind of transformation that those corrections are trying to capture. So for one tool, and for a particular task, what is it about the tool that's most important? Well, is it the transformation in the translation space, or is it the transformation in the orientation that matters from one tool to the next? And so this transformation can then be applied to a trajectory and planned from the original model. So if we're playing, so this is the original demonstration in the paint with the paintbrush. Oops. Okay. So now we have the paintbrush is playing the original demonstration, and the cup is the transformed trajectory that we now can plan based on taking the paintbrush trajectory and transforming it with that pose correction that we learned from the humans' corrections. And so that we call this kind of within task transfer. So we're able to transfer the paintbrush, the sweeping task, with starting from a paintbrush, getting to the cup. But what's really interesting is to understand, what we're asking next is whether or not the fact that I've learned something about a task that was done with a paintbrush and now is done with a cup, can I do other tasks that I know how to do with the paintbrush and now do that with the cup? And so that's the question so can we generalize without additional corrections to a completely new task? And so here's an example of the hooking task, and now the cup has a pose correction model for things that I know about paintbrushes. The paintbrush as the tooltip, I correct with this kind of a transformation in order to do them with the cup. So this is exciting and is the kind of efficient use of humans that Tesca is really working on, and being able to leverage something about the cup itself and the paintbrush itself in order to transfer to completely new tasks. And so we're interested in whether or not the within task evaluation is being able to transfer a corrected task with the new tool, and that we have very high corrections. It's over 83% accurate, and then a cross-task transfer, so being able to do a completely new task with the tool that you've never seen that task before, is currently about 30% accurate. So there's something about, there's some tasks for which that transfer works and some tasks for which it doesn't. And so the current work that Tesca is doing is kind of digging in to understand, which tasks does this transformation really work and which does it not. Further improvement is seen when you analyze the task to understand something about whether that translation component or the rotation component of that transformation is going to be the dominant one. And if you do a little bit of mapping task to kind of translation versus orientation, then we can get the transfer rates to be up to 50%. But again, that's with not a single demonstration ever on that task. You're still 50% accurate at getting it done with a completely new tool. So I think those are pretty exciting. So what I'd like to kind of pop back up and talk about what we're really, our goal is to think about how we're going to get robots to learn from human teachers and be able to kind of jump into human teams like this and be able to learn on the job after they are deployed in the world. And I think all the robot learning work in my lab has been focused on this overall goal of really getting human teachers to be able to tell robots what to do and have robots be able to understand that. Since I thought it would be interesting to kind of dig up the very first example of robot learning, I kind of realized as I was going through this and giving this talk, especially since I've given a Robotics Institute seminar before, I was like, oh, how's my trajectory or my lab changed or not? And I think I was telling some of the students at lunch today, I was like, no, I've pretty much been obsessed with the same problem for like 15 years now. And so I actually have video proof of my obsession with the same problem, and I'm going to share with you now of this So this is the first robot learning project that I ever did, and this is Leonardo at the Media Lab at MIT. Somehow all of my videos need to be played 2 times. But and so this is one where press the red button. Leonardo has very few manipulation capabilities, but is good at pressing buttons. Turn all the buttons on. So that starts a learning process.
Teach you to turn the buttons on.
That's called Turn the Buttons On. It has a label now called Turn the Buttons On.
Press the green button.
And now the robot's recording each action that it's being asked to do. So it's learning from demonstration.
Now all the buttons are on.
So that closes the task, and so now the robot builds a representation of okay, what were the preconditions, what were the postconditions, what were the actions I was asked to do?
Can you turn the buttons on?
And it says, yeah, I can achieve this. But it shows that it's not confident because it's only got one example. So it's looking at the person to show lack of confidence.
Not quite. Press the red button.
And so then this turns into a correction. So now I have 2 examples of doing this and the pre and post conditions of the whole task and the individual actions.
Now all the buttons are on.
So the most likely hypothesis, given the data, is that every object called button needs to have the post condition on.
This is the blue button.
Whatever happened to that robot?
Have you learned to turn all the buttons on?
It's sitting in a corner at the Media Lab. Yeah, kind of like museum style.
Have you seen all the robot movies?
I know, I was going to say, not unlike the robot museum I saw.
Much fancier one at MIT. They have a real MIT.
I know. Leonardo has not been upgraded to the actual MIT museum.
Yeah.
Kismet is there. Okay, you guys get the idea. But so I have been obsessed with this idea of a robot being in a social interaction with a person and learning on the job and getting the right information out of that demonstration. And so I think it's fun to look back at the some of the things that are the same and some of the things that are different about the goals of what we're trying to achieve. But really, I just strongly believe that adaptive manipulation skills and adaptive skills in general and robots being able to adapt their skill set in the situation that they need to interact is going to be the key for getting service robots into dynamic human environments. I don't see any other way around it. Somebody could prove me wrong, but I just really think that's what we're going to do. And if you look around the world, there's so many sort of things that the robot's going to have to learn how to operate. It's going to learn how to operate door handles and lamps and buttons and switches. And the thing that I think is the key observation, though, is that the service robot that's going to be in your home doesn't need to know how to operate all lamps in the world. It needs to know how to operate the 2 different kinds of lamps that you have in your house. And so there is the opportunity to have that be a learning experience that happens in the situation, and then you have a very specific skill set that happens in that context. We think this is going to be a key factor to getting robots out into human environments more quickly. And with that, it kind of takes me to my next chapter, which has been all about getting service robots out into real human environments. So this is my company, Diligent Robotics, co-founded with my former Ph.D. student, Vivian Chu, right here, who did a lot of exciting work on learning haptic skill representations from demonstration in her Ph.D. and is now the CTO of Diligent. And what we're doing is putting robots into hospitals to assist clinicians and nurses and really try to give clinicians and nurses back more time. And so we are, in general, we're interested in having service robots that are going to empower teams that can kind of function as a teammate, take on some of the menial aspects of work, maybe the chores of work, and let people do some of the more highly skilled aspects of their job. And so in hospitals in particular, there's a lot of menial tasks that are hunting and gathering and fetching and delivering that currently nurses and clinicians are doing, and we don't think they should be doing that. Nurses and clinicians are burning out of their jobs because of all of these overtasking, and so we think there's a real opportunity to help hospitals. But Moxie is a mobile manipulation social robot that is, like I said, designed to operate side by side with people. So it's got a small enough footprint that it can go everywhere that people go in the hospital. It can go into small, clean supply rooms. It can grab things out of bins. And what we do is, given that we have an arm, unlike some other mobile robots that have been deployed in hospitals, we, instead of just delivering from a person to a person, we can deliver from a place to a place. And it sounds really simple, but it really kind of changes the category of tasks that we can ask the robot to do to support nurses. And so as one example, whenever in the electronic health record a room is marked clean, then Moxie will get a trigger to set up the room for the next patient. And there's a set of 10 things that need to go in every patient's room. And it's really annoying for a nurse when you've got a new patient who's coming in, you get to the room and you realize that nobody put all the stuff that you need for, they don't have their welcome bucket. And so Moxie doing that takes that off of the plates of anybody in the frontline staff. And we would hear things from nurses. We're now out in kind of pilot testing, and we hear things from nurses like, well, I don't think I ever saw Moxie do the task. It was just, I see Moxie around, but I didn't see her doing the room setup task. And, it just was great the whole month. I didn't have to ever think about that. It just got done. And so those are the kinds of things, the opportunities to improve workflows that we're looking for is, how do we give things to the robot that are, simple enough that today's technology in terms of mobile manipulation can do it, but important enough that it really reduces that cognitive load of the nurse. So that kind of proactive autonomy in the environment. And I want to I can just show a video of some of the things that we've been doing. And again, I'm probably going to have to do this. It's the Canova Jaco 2, which is, it's good. So, essentially we are delivering things that are, trying to get things that clinicians need closer to the point of care. So we're bringing things, and if there's either a drawer that Moxie will drop things to, or if there's not a drawer, it'll be a mailbox. We can also do lab deliveries. We have a little lockbox that we've stuck on to prototype doing lab deliveries and pharmacy deliveries. And Moxie will use its facial expressions to kind of indicate where it sees people, where it's going, doing social navigation, to have places that you get out of the way. One of the tasks, you want to keep the clinicians in the room. So one of the things Moxie does is when somebody's changing a patient's bed, Moxie will stop by to actually cart the soiled linen away. There's actually a lot more requests for social interaction than we thought. We end up we don't go inside patient rooms, but we get a lot of requests to come just outside of patient rooms and have a little selfie time and wave. But here's the only time that the robot does go into the patient room is to kind of deliver a set of supplies for a new room setup. But a lot of times nurses will find Moxie in the supply room, putting together kits of supplies that are needed for different clinical care tasks and having those kind of ready to go whenever those triggers are received.
Do they catch it smoking?
That would be a good one. Great. So that's like a little overview of Moxie's greatest hits. Yeah.
So have you had the chance to apply any of the learning from demonstration or on Moxie with clinicians?
So so clinicians are not teaching Moxie, but Moxie is learning its skill set on site. And that's key to the solution. Yeah. Uh-huh. Yeah, so we wanted the face to be, it's intentional and not. The primary way that it's holding its arm is within the footprint of the base, so that it's not increasing its footprint with its arm. But then also we have it here instead of here, so that you can have social interactions in the hallway. Yeah. Yeah, but already we get a lot of comments that it looks like Moxie's making a rude gesture. So we had to actually start holding it like this so that it wasn't. But there was one like really colorful nurse who was like, she's like, I like it. It's just walking around here like, everybody, you just screw you. And then, she was the first one who really mentioned it, and then everybody started mentioning it. And we're like, open the gripper. Yeah. So, but just like where we're at, we are in a pilot testing phase. We're in pilot tests with 5 different hospitals across Texas. These are 4 of them that have already started. Here's our first group of nurses that we deployed Moxie with. The pilots are for a whole month. A single robot gets deployed and is servicing one hospital unit, and we help them understand, look, this is what a workflow looks like, reimagined with robots. And then that kind of starts the conversation of how to do a long-term implementation. Yeah.
What's been the most unexpected challenge of the pilot?
So, a big part of what we were trying to understand is what should the robot really do to drive the most, to have the most impact on getting nurses back to the bedside, for example. And so, the challenge has been looking at, what are the things that the robot can do that are similar across settings, that are common enough that it makes sense to have as a feature of the product, really, instead of just like a one-off thing for this hospital. So one hospital, really wanted us to deliver water to all the patients twice a day, but they're the only ones who asked for that. So then you have that challenge of product decisions of do we have it deliver water? How many people are really going to want that? Is that a nice to have thing or just really valuable? And the other is, I think, by definition, we are disrupting a workflow. We are disrupting the nurse's normal workflow, and we're saying, hey, you don't have to do that anymore. Moxie's going to do that, and don't run to the supply room and back and get that. And so, in a sense, it's really hard to break a habit. And so a part of what we do over the month is kind of track utilization of the supplies that Moxie is bringing. And, we have these graphs that are like, it starts off in week 1 and everybody forgot that Moxie was even there. There was even a mailbox. They see Moxie around and they're like taking pictures with it, but they don't like remember that Moxie's actually bringing things to this drawer or this mailbox. And so there's a lot of kind of education about what Moxie's doing. And then, so we usually use like week 3 as our benchmark of how it's doing. Yeah.
Do you extend the interface to everybody's cell phone or TV in the room or any of that?
So currently, so that the question before that is, can people interface to Moxie and tell it what to do? And currently, we are focused on having Moxie infer what to do based on routines and triggers from the electronic health record. So it's not that a nurse says, Moxie, go get me IV thing. So.
You're doing the harder thing first.
Well, so just in time, there's different operational problems, right? Like it's a different, so if I know that every day at 7 a.m., a certain set of supplies are needed, I just have to make sure that happens by 7 a.m. Versus if at 7 a.m. I get a trigger like, Moxie, I need an IV start kit, stat. Like how much time are people willing to wait for that? And how quickly can we respond to it? So in one of the pilots, we did have, well, I guess in all of the pilots, we have experimented with a little bit of just-in-time delivery, just to kind of see what our response times can be and whether those are fast enough. So I think it's still remains to be seen, like whether it's fast enough when the nurse says, Moxie, I need this, for the robot to toddle over to the supply room and back, and that to be good enough.
Right, but there are intermediate tasks. Can you change these flowers that are cut?
Yeah.
Which can happen anytime.
Yeah. Well, and those, so we are experimenting with ways that the nurses could actually tell us what to do in that, and have them be less immediate.
So a couple of the applications you showed were of that character, like deliver this medication or this, whatever, or come and get these patients.
Yep.
I mean, that's not something you can infer. Presumably, that's not something you can infer anything.
No, and so like the bed sheets one, we have a designated spot outside the door that they can set it, and it's not necessary for Moxie to meet the person there to get it. So it can be delayed by however long, and Moxie just does lapse to find them. Yeah, but the lab deliveries, you do have to set a time. You have to be called over. Yeah.
So with Moxie's river, does it need to be disinfected between tasks? And if so, how does Moxie do that autonomously?
So Moxie doesn't currently do that autonomously. For the most part, we do clean tasks and we stay in clean spaces. So then the robot needs to be cleaned as often as any other computing equipment device. So like the workstation on wheels that they have in the hallway have to be wiped down a certain amount of times, and we do the same.
So going back to the previous topic,
Yeah.
the paintbrush.
Yeah.
So you have no semantics. There's nothing that says, wow, what's important about the paintbrush is a flat surface or a flat line of contact.
Right.
Are you going to work towards that?
Yeah.
That really gives you generality.
Totally, and that's the next thing, and that's basically the reason that just blind transfer, where you're just looking at the pose, coming up with that one pose transformation that you should apply across the whole trajectory based on a new tool, is it only works about 30% of the time, and it's because we don't have a nice semantics of the tool, and that's going to be the next thing. Yeah. Chris.
Well, no.
Okay.
So a lot of the demonstrations or a lot of the videos that you showed have like demonstrations which are given verbally, right? And that requires like a grounding for things to happen. So I was wondering like if there is like a way, or if you guys are thinking about something, how do you ground these symbols autonomously rather than you telling like what pressing actually means?
Yeah.
So is there a way
Oh, so like the very first like button pressing. Yeah, that was super, there was no learning of grounded symbols. So I wouldn't say we have anything very well formed in that. I think there is a huge opportunity while the person is giving a demonstration to have them talk aloud and have them label things and have them, so we've done, actually Tuska Fitzgerald did a small exploration into, getting people to explain what they were doing while they were giving keyframes. And it's clear that some keyframes are more important than others. Some are, well, I'm getting ready to get this cup, and so here's a preparatory action versus something that is about the constraint. Like once I have this, the person might be talking about how we're going here and we're keeping it upright. So there's different things that the person's talking about during the task. We have a data set of that, and we haven't done very much of it with it. And I think there's a lot of opportunity to kind of do some supervised learning of groundings of language and skills. Chris.
I understand the need to get the words deep learning into every talk. I can't figure out why you are using deep learning to tune your simulator. It seems to me any optimizer, your favorite optimizer, would
Sure.
happily jiggle the parameters until
Yes.
you match one thing and another.
I would completely agree with you. So the thing that makes it work is what you're optimizing, absolutely. And it happens to, that's the students' favorite optimizer these days is a deep learning network. But the real key is like saying that, I actually don't want to have anything about the parameters themselves being what I'm optimizing. I want to look at the output of the simulator and, output of some target model, output of the proposed model be what I'm, I train that network to be able to tune these two when I know what the real reality gap is. So I take a simulator and I make it like,
We call that system identification.
Yeah.
Yeah.
And it's just doing it really fast and compared to using an RL approach that's very task-based. So it's kind of in response to some of these works that are out recently to do this in the context of a particular task with reinforcement learning and saying, look, it's a better idea to just do that system identification with your physics simulator.
How do you deploy the robot? Like, do you have to tell it go slow over some cracks on the floor? You have to tell this area might be sunny, so don't use your LiDAR. How does that process work? Does it take a while to deploy?
It doesn't take too long. We do have to drive it around and build a map of everywhere the robot's going to be operating, and drop down. We drop down like waypoints of important locations, and we set no-go zones. Essentially, yeah.
So how do you know you're optimizing the right thing? For instance, how does the system know to optimize the coefficient of restitution of the ball rather than the bouncing into the floor?
So
How much
you have to tell it the parameters that you're optimizing. After you have that network that is trained to bridge a reality gap between a simulator and the real world. Does that make sense? I guess I didn't.
Let's thank our speakers.